Good afternoon, everyone. Welcome to our spring quarter ITS seminar series. Before I introduce our speaker today, I want to go over a few things about this seminar. For all the audience, I think this seminar series is also a class for some of our students. So for those of you who take this as a class, I would like to remind you that you need to complete 7 assignments through Canvas out of the 8 seminars. So you need to submit your assignment and answer within Canvas. For questions, we would like you to hold your questions till the end later and till the Q&A session. If you have a clarification question, you can raise your hand. Otherwise, we'll leave the questions to the Q&A because we have also audience from outside, and for you that you can only raise your question through the Q&A function. But for our students, we would like you to have your questions through chat, the Zoom chat function, and you can post those kind of questions at any time and not necessarily by the end. So that's a few things to tell our audience. And now I would like to introduce our speaker. So today we're very pleased to have Professor Sharon D as our first speaker for the spring seminar series. Sharon is right now an associate professor in the Department of Civil Engineering and Engineering Mechanics at Columbia University and in New York City. She received her PhD degree from the Department of Civil, Environmental, and Geoengineering at the University of Minnesota and did her postdoctoral research at the University of Michigan's Transportation Research Institute. So Sharon's research lies at the intersection of game theory, dynamic control, and machine learning with applications to emerging transportation system optimization and control, shared mobility modeling, and data-driven urban mobility analysis. She directs the DTAC lab and serves on a committee for the Smart City Center in the Data Science Institute at Columbia University. She is a recent recipient of the prestigious National Science Foundation Career Award and a winner of the Transportation Data Analytics Contest from the Transportation Research Board. Her talk today is on dynamic driving and routing games for autonomous vehicles. Sharon, the Zoom room is yours.
Thank you. So first of all, I'd like to thank Professor Zhang for hosting me today. My name is Sharon D, and I will talk about some ongoing work in my group using the mean field game. And this is a joint work with my students, Xu Chen, and my postdoc, Rongye Shi, and also student from math, Kuan Huang, and also professors Qiang Du and also Xi Chen from math and computer science. So Professor Zhang just talked about my career path. So now I just quickly go through it. So I did my postdoc for 2 years at the University of Michigan before I moved to Columbia. And then at Columbia, I direct the so-called DETECT lab. So the full name is Data and Innovative Technology Driven Transportation Lab. So I call my students in my lab detectors. And this technology I want to focus on today is the level 5 automated vehicles, or we call it autonomous vehicles or driverless car. So there are multiple names attached to it. For technology, it's actually a double-edged sword, which means it has the positive and negative sides. From the positive side, the autonomous vehicles are claimed to improve the traffic efficiency and safety. And on the other hand, when they interact with the human drivers on roads, so we call it mixed traffic, then it may produce these unprecedented consequences, like what we observed that the Google self-driving car have crashed into buses and also other cars. And also 3 years ago, the Uber car killed a pedestrian crossing the street at night. So my research is focused on transforming the technology for social good. So because I focus on this autonomous vehicle, let me show you a video to see how this technology may need to be improved to better interact with human drivers. And the traditional approach to model self-driving cars is to treat them as a control agent. So what I mean by control is that they follow some mathematical formula, basic equations, and then they are dictated by these dynamic systems, such as the ordinary differential equation. However, in this video, I will show you when the Waymo car is put onto the public roads, and then you can observe some very awkward phenomena. So this video was uploaded by some Twitter users. Sorry. So you can see this car is webcam is recording is how Waymo car tried to merge to the highway. So you can see it's left the blinkers on. And I think this is in California. And all the human-driven cars in the neighborhood were able to merge in. But then this Waymo car failed to find a gap. And then eventually he had to actually get off the ramp and gave up in using the highway. So from this, maybe there are many this kind of videos actually in YouTube. You can search. It's from the human perspective, probably we don't really understand why they behave either conservatively or differently from what we expect. So that's why we project that in the future, we should model autonomous vehicles as AI agents. So AI is the artificial intelligence. So what do we mean by AI? So first of all, they should be a rational utility optimizing agent. So they should behave rational as what the humans behave in most situations. And then they may play a cooperative or non-cooperative game with the road users in their neighborhood. And they should develop this learning and adaptation capability to navigate in a complex traffic environment. So that's why I believe in the future, the AV, which refer to the autonomous vehicles, and HV refer to human-driven vehicles, and they will play a game on these public roads. And we really need a game theory to empower the driving intelligence of the autonomous vehicles. And in this talk, I aim to answer several research questions. Basically, if in the future we bring multiple autonomous vehicles, or a large number of autonomous vehicles to the traffic networks, the first question we want to understand is, what are the optimal control problems we can formulate for an autonomous vehicle or AV? And here I will talk about how we use game theory to model each car's speed choice and also the route choice. However, we know that in a road network, there are many other cars that also exist. So what if everyone tried to optimize its own while others doing so simultaneously? Then this forms a game. So we cannot just model one AV in an isolated fashion. We have to look at them in a multi-system, a multi-agent system. And also the third question I aim to answer is, if it's a mixed traffic scenario, so how the human drivers should be modeled and how they interact with the autonomous vehicles. To answer these questions, so in this talk, I will introduce how we borrow the game theory, control, and also the machine learning to study these three research questions. And in the rest of the talk, I will touch on each component one by one. So let me describe the setup of our work. Assume this is a ring road, and then there are several AVs that are running on this road. And through basically in the first component, I will introduce how we use the game theory to control many cars in an efficient and scalable way. And then this game theory model turned out to be kind of like a new traffic flow theory to model how AVs will be controlled on roads in the future. First way, because we assume that AI agent, which means they should have one objective function or reward function they need to optimize. And then we introduce this objective function called J. So it's composed of this F function over time. So we call it the cost function. So this cost function depends on the speed and also the position of the controlled car. And it can contain the terms that represents one car's running cost, congestion, and also safety cost. Even we can include terms that reflect the emission. And this V of T represents the terminal cost. So what's the cost that we want this car to achieve at the end of the planning horizon? And for this n-car differential game, so each car solves the optimal control problem and at the equilibrium. So when other cars hold their driving strategies fixed, then this car's strategy, which we call it Vn with respect to time, should achieve the minimum travel cost. So that's the meaning of the equilibrium in this game. However, when we increase the number of AVs on the road, when their penetration rate increased in the future, so this problem actually becomes not scalable. So how we can control so many cars and move them on roads simultaneously? So that sounds like impossible work. So what we did is instead we borrowed this concept of so-called mean field game. So mean field game actually aims to model complex multi-agent dynamic system when the number of agents involved in the system goes to infinity. So in other words, so this game actually is a non-cooperative niche game with the player number go to infinity. And this game was proposed by a group of economists and mathematicians. And since then, they were able to explain many phenomena, for example, this Mexican wave. So what Mexican wave describes is when in a big stadium, a lot of audience there, when each of the individual agents, they do this stand up and sit down movement. But aggregately, you found out that their collective behavior generate a wave that move horizontally across the stadium. And then this game also can successfully explain some natural behavior in animals groups, such as fish schooling. The reason that this game becomes so successful and widely adopted since its inception is because it can link this microscopic agent-based behavior to the macroscopic collective behavior of mass. Okay, so our question is then, how do we implement this idea to the traffic control? So this is what we want to do using so-called mean field approximation. So still, let's come back to that ring road scenario. For the ego car N, we want to control its speed, and then we assign some predefined objective function J. But when we apply this mean field, which means when we increase the number of agents on this road, so then actually this car, every car become like homogeneous agents, and then we can ignore their index. And then we treat this car, we try to control as a generic car. The cost function is remain the same. However, instead of interacting with every individual car, so this car can only perceive the traffic density in its neighborhood. And then this game actually is transformed, and we just need to calculate the so-called mean field equilibrium, which is characterized by U star and rho star, which is the velocity and the traffic density in time and space. So we call the density field and the velocity field. And to solve this problem, it has to employ so-called forward-backward structure. We start from agent dynamics, so individual car. They try to react to the older cars in the neighborhood and minimize objective function J. But once we apply this mean field approximation, then their objective actually only depends on its own speed and also the traffic density. Then assume we know the speed of that car, then we can feed it back to so-called mass dynamics, which is the rho t plus rho u x equal to 0. So this is the flow conservation equation we always use in the traffic flow theory. Then when we give u, then we can solve the rho. And then we feed this rho back to the agent dynamic. So we update the traffic density in the traffic environment, and then the car will adjust their speed accordingly. And then we do this back and forth, eventually reach an equilibrium. And then basically we need to solve two equations. One is the HJB equation solved backwards that actually describe how individuals solve an optimal control problem. And then on the left-hand side, we solve the so-called FPK equation, which is solved forward to derive this traffic density. So when this process go back and forth until it converges, it reaches so-called mean field equilibrium. So I will skip all the details, but let me present the results. We compare the scenario when the AVs are controlled by this mean field game versus when they are driven by the LWR. So LWR is a first order traffic flow model widely used in transportation. So it basically you assume a fundamental diagram, and then you assume the density and velocity field evolves according to some flow conservation equation. And as we mentioned, we need to first define or predefine this cost function. So we found out that the LWR actually can be reinterpreted as a mean field game with this cost function. So U rho minus U divided by UM square. So UM is the maximum speed. So this difference actually means that under the LWR model, cars their goal is to drive their speed towards the equilibrium speed, which is defined by some fundamental diagram. So based on the understanding of this LWR objective function, so we add one term, rho j minus rho divided by rho j. Rho j is the jam density. So this term actually represents that the car also try to avoid the crowds. They try to ensure that the traffic density deviate from the jam density as much as they can. So by adding this additional term, we found out that the traffic flow exhibits very different patterns. So let's focus on the figures on the bottom. So the left one is how the traffic density and the speed evolves. So under the mean field game. The right-hand side is when the density and the velocity evolves under the LWR model. So you can see at the beginning, the position of the cars on the ring road are exactly the same in these two model scenarios. So we deliberately put more cars in this neighborhood to generate some uneven distribution of the cars. Let me play this video. So you can see as time goes on, and the left-hand side, this jam area gradually actually smoothed out. But on the right-hand side with this LWR model, a shock wave emerges here. So from the upper animation, you can see that. So this area still we can see the traffic jam. sorry, not this area, this area. So the color of the this rainbow represents the density. The darker means the more congested. But on the right hand side for the mean field game, you can see the traffic eventually move towards the uniform flow. So that tells us that mean field game, so by carefully designing the reward or objective function of the game, we can actually better manage the traffic flow in the future when we have the autonomous vehicles. And also we found out that LWR can be treated as a special class of mean field game, and with the objective function being the everybody trying to move towards the equilibrium speed that is defined by fundamental diagram. The second, actually, LWR can also be treated as a myopic mean field game, which means if the car only optimizes velocity based on the density in its neighborhood at current time, so then we get LWR. But for mean field game, so cars can basically anticipate the future traffic condition and adjust their speed accordingly. So this is the first part of my talk. So we basically designed this mean field game to model how autonomous vehicles can be controlled in the future. And for the second part of my talk, so I will move forward that from this ring road to the transportation network. And also similarly, I will compare how mean field game how the cars driven by mean field game exhibit a different pattern from those driven by LWR. I will skip the details, but let me introduce the setup of this model. So this is the road network we try to look at. So it's a very simple small network. We call it the breeze network. So it contains 4 nodes and with the 5 links. And we assume there are traffic demands coming from the road 1 and 2. And the objective function we use here contains 2 parts, the running cost and the queue cost. So the running cost is composed of 3 terms. The first term actually defines the kinetic energy. The second is the safety. So basically a car try to avoid the congestion. And the constant part, when you put it inside the integral from 0 to t, actually it represents the travel time or driving efficiency. And we also introduce a queuing cost. So the reason we have a queuing cost is because when the flow from node 1 and 2 may meet at node 3. So then if the incoming flow exceeds the capacity of the node 3, then some queue may form here. And I will compare how the traffic pattern evolve under LWR and mean field game models. And here I will show you 2 figures. The left is the density rho, the right is the velocity u as time moves on. And then I mainly showed how the flow along this path 1, 3, 4 evolves as time progresses. So yeah, we inject the traffic demand around this time. And if we run it under the mean field game, so you can see the pattern is quite different. So I want to point out the difference, which is here, the peak that emerges under the LWR model. So this is because when the flow coming from the node 2 meets the flow from node 1 at the node 3, and their some of the flows exceed the capacity of node 3. So that's why there's a queue basically sitting there, cars, but we assume it's first in, first come. And because of the queue, so the velocity actually dropped in a similar area for the velocity. But if you look at the mean field game, this doesn't exist. So the reason is the mean field game actually can control, through the mean field game, we can control how fast a car drives on a road. So we deliberately actually let the car coming from node 2 to 3 slow down so that they don't have to meet the flow from node 1 simultaneously. So that actually mitigated the flow peak, and then the whole traffic pattern is mitigated. So from this, we can see that the traditional traffic model, like LWR, it assumes the car speed is controlled by density. But now we introduce this game that will enable the car to further control their driving velocity on each road. So then that provides a lot more freedom to the AV control and also can help mitigate the traffic flow. Okay, so this is the second part of my talk. First, I introduced what's the new equilibrium it can achieve in the future if we replace all the cars on the road by autonomous vehicles, and how they can move on road networks by both selecting their speed choice and route choice. So in the last part of my game, the talk, I will introduce how we can leverage the data that collected nowadays from the AVs and also existing sensors to better model human driver behavior and how humans interact with the autonomous vehicles. So this is an ongoing work, so it may be a little disconnected from the first two components. First, I will talk about the, We leverage this Waymo car data that was publicized, I think 2 years ago. So basically, the Waymo shared some of the data collected from their camera and also the LiDAR that mounted on the top of the Waymo cars. The left is the camera image, and the right is the LiDAR point cloud. And then we aim to leverage these new data formats for driving behavior modeling, because the purpose for Waymo to publicize this data is to actually for the computer vision community to better develop efficient algorithms for the object detection and tracking. But we think that maybe we can use this data to also better understand how Waymo car is programmed to drive. And so for this work, I don't know why this box showed again. Yeah, so we fade in basically the right-hand side of this video was captured from the camera of the Waymo car. So from this camera, we can extract the distance from the leading car, which is the white car in front, and also speed difference. And also we use these images as input and feed it to a machine learning toolbox. Here we use long short-term memory model, and then we try to predict the acceleration rate that the Waymo car will adopt. So here is actual position of the Waymo car. The orange one is the predicted one. The red car is actually the white car in front of it. So we use this can capture actually the car following behavior of this Waymo car with a reasonable error allowance. Through this, I want to show that because the image data and also the LiDAR points data are not traditionally handled by the transportation community when we try to model car following or lane changing behavior. So that's why we have to resort to the machine learning models. However, another message I want to convey is that so this machine learning or black box tools sometimes may fail, and also it seems like a conflict from the domain knowledge we have developed. For example, in our transportation community, there are like a large number of models that have been developed in the past decades. So how we can reconcile the machine learning model and the domain knowledge I think is also a promising direction we should explore. Machine learning can help discover some mechanism from the data that collected from the domain. However, they require a huge number of representative samples to train. On the other hand, if we have already discovered certain patterns which satisfy some physical constraints, then probably we can also supply those domain knowledge into machine learning tools to better train this model. So let me compare this so-called, we call it physics-based model and also the data-driven model a little bit in this diagram. So the x-axis represents how much data the model type uses, and the y-axis represents how much scientific theory it uses. You can see for the existing physics-based model, so all the models that developed, mathematical model developed in transportation, we call it a physics-based model. So they use very small number of data, but they highly rely on our scientific hypothesis. On the other hand, the machine learning models, they highly rely on purely rely on the data, and without even knowing what's the physics hidden in the data set. And now there's like a growing area called physics-informed machine learning. Basically, try to leverage the advantages of both physics models and machine learning model, and so that we can train those machine learning models using the knowledge of the physics. And let me give you an example of how this idea can be applied to traffic flow, traffic state estimation. Actually here, sorry, let me reshare my slide. It seems
Sharon, yeah, maybe we can pause and then you can reshare so we can move that yellow box from the screen.
Actually, I was doing, myself and Christina were looking at this, and it looks like it's a setting in Zoom that needs to be changed. And it's actually not an easy setting to get to. It has to be done within the Zoom settings themselves. It looks like this may be something that just is a new thing that we're coming across, possibly due to the update. But Christina, can you privately share that link to Sharon? And we'll pause the recording right now. Privately share the link to Sharon so she can go ahead and uncheck that setting in Zoom.
Yeah, sorry for the interruption. So let's come back. Basically here, I want to show you how we can train a neural network to approximate the solution of a partial differential equation. And this is the partial differential equation we try to focus on is rho t plus nx of rho equal to 0. So this nx is a nonlinear differential operator. It can be any form that depends on rho. And then rho can be any physical value we are interested in. In the traffic flow, usually we are interested in density or velocity field, defined by the x and the t, the time and space domain. And then we define a residual, which is just the left-hand side of this equation. And if our goal is to train a neural network that approximates the solution of this rho of tx, then we at this optimal solution, the residual should be equal to 0. So how do we train a neural network? Because we know that the key of training a neural network is the loss function. So here we define loss function as two components. The first is the mean square error of the observed data from the predicted value. And the second, we introduce a new term, which is the deviation of a predicted value on the co-location points. So the co-location points actually are related to the physics I'm trying to refer to, and I will explain to you in the next slide. Here I just use a simple example. So the PDE model we try to solve is LWR listed on the left top left corner. So rho t plus the rho u with respect to x equal to something. So usually we use 0 on the right-hand side, but here I introduce that viscosity term to make the solution smoothed out. And we use the Green-Schultz fundamental diagram, which is basically define a linear monotonically decreasing relationship between the speed u and the density rho. And we define some initial and boundary condition. We assume this is on a ring road. So you can see this heat map actually is the solution of the rho Tx, the density field in the x and the t space time space diagram. And here we define our observed data. Assume we place some loop detectors at certain locations. So because the loop detectors are fixed, so that they can collect the data continuously along that direction. And then assume we can observe all the density data in those specific location and across the time. The collocation point here is actually you can randomly sample those t and x from this field defined by the x from 0 to 1 and the t from 0 to 3. And on the collocation points, we will calculate the value from that PD model. Assume we know this is the physics we want to use to train our neural network. And then we define a loss function that is composed of these two components. The first, the MSE rho, is the deviation of the predicted value from neural network. The deviation from the observed density that collected from loop detectors. And the MSEF is the residual or the difference of the physics value we calculate on these black cross points. And then we train a neural network and we produce the whole density field. You can see the lower bottom, this figure can actually, this heat map that represents the predicted density field is almost the same as the exact rho Tx that solved from this LWR model. So this is a demonstration. Assume that we know exactly the physics that generate data, then we can train a neural network that produce the solution of the PD exactly using those only some sparse observed data. We also apply this work to the real world data set, which is the NGSIM data. The NGSIM data was collected on 2 highways in California. Basically, they mounted some cameras on near some buildings by the side of the highways, and then extract all the individual vehicle trajectory in a specific segment for a specific time period. And then we, using all the vehicle trajectory data, we can aggregate them and calculate the density field here represented in this heat map. We call it rho Tx, which is the density field along the time. Basically it's 45 minutes, and x is roughly 600 meter segment. And assume we place several sparse loop detectors along this segment. And here I will mainly point out one finding we have. So on the bottom of the figure, the x-axis is the number of loop detectors. So we increase from the 2 all the way to 18. Basically, we evenly distribute all these loop detectors. And we train a neural network. And we use also some LWR model as the physics to help us better train the neural network. And then we do the prediction. And we found out that as the number of loop detector increases, basically the more observed data we get, actually the less we rely on the physics. So the beta is the weights in front of the loss term in front of the physics, and alpha is the loss term, the weights in front of the data term. So when the ratio of beta over alpha decreases, which means when we have more and more observed data, we more rely on the neural network to predict the traffic density and less rely on physics. However, when we only have 2 or 4 loop detectors, then in this case, it's very hard to train a very good neural network because usually it's basically requires a huge number of representative data. Then in this case, physics actually play a better role. If we have a more accurate physics, we can still use so sparse data to make a better prediction. So that's all about my talks today. Let me make a summary. So my research mainly applies the game theory, control, and machine learning to better understand the traffic patterns with the emerging transportation technology. But there should be some convergence about these different fields. The one question I'm very interested in answer is what are the new equilibrium in the future when we introduce these autonomous vehicles or the other road user that we've never seen or model before. And the second question I'm interested in answering is how we can leverage the technology to better manage our traffic flow. So these 3 fields should not be isolated. And hopefully we can also merge the game theory and machine learning, say, to close the loop. As I think now in the game theory field, people are trying to also study this learning in game. It's not a new field, but I think more and more people are trying to look at the convergence between the reinforcement learning and also the multi-agent reinforcement learning and how agents play games in the system. And on the other hand, whether the machine learning can be also incorporated into control field, so-called learning-based control. So assume we don't know exactly how the dynamics, the environmental dynamics evolves, whether we can borrow machine learning to learn these evolving states of the environment and better come up with some better reliable control. So that's all about my talk today. Thank you very much.
Thank you, Sharon. I think we'll open up to, now it's the Q&A session, and we'll open up to questions. Again, I would like to remind, for our student audience, you can raise your hand to ask your questions. And for our outside audience, you can use your Q&A feature to ask your questions. So as a host, let me take advantage of being a host and ask the first question. So Sharon, you're being very successful in navigating the early career of a faculty. Many of our students aspire to become academics and faculty in the future. Maybe you can use the first question. Perhaps you can share your experience as assistant and now associate professor, and how to to be successful finding the academic job, and also in the first few years how to life and how to make it work.
Yeah, thank you for this question. I think Professor Zhang, you are the perfect person to ask this, because I think you watched me growing up. You witnessed almost my entire career path. So I met Professor Zhang when I was an undergrad at Tongji University. So that time, actually, I didn't know what to do. I was very uncertain about my future. But so far, I still remember one thing that Professor Zhang told me. That time, because I was wondering whether I want to, after graduation, whether I want to stay in China to go to work, or I want to study abroad. During the conversation with Professor Zhang, so I raised my concern that I feel I'm too old that time. Like I'm not sure whether it's still the right time to like prepare those GRE exam and then go study abroad. And even I go abroad, I may not know what's my future like. But he told me that it's never late, and you are still young, so you'll have time to prepare and fight for your life. So I think that really made me determined to work hard and prepare for everything. And then even after I came to the US, I think basically during my graduate school, especially I think after 2008, because the economic crisis and transportation actually was the graduates from transportation that time I think had some hard time in finding jobs. I think not only this field but also all the fields faced that challenge. So that time I was also not uncertain whether I want to pursue this field, but I'm happy that I insisted, because when I was in the job market, probably after I graduated in 2014 to 2016, these 2 years, actually we see a tremendous increase in interest in transportation, especially I think thanks to the advance of the communication and also sensing computational technology. So that's why Columbia hired me because I was the first one in transportation at Columbia. Previously, they may probably not think that transportation is like an essential piece of smart cities, but then they see that the trend and then they decide to include people. They realize smart transportation is basic integral part of the smart city. So I think my advice for you is to never give up. And when you feel desperate, then talk to those senior and wise people for their advice. I think sometimes one of their just a sentence can change your life.
Well, thank you for sharing the personal experience. I think 2008 was a hard time, and now we have the pandemic. So this is particularly relevant because some of our students going to the market may find it very challenging. And as you said, the perseverance and patience eventually will pay off. And yeah, so let me open the chat room. A couple of thanks and no questions yet. So any questions? You can okay. So Juke, you can turn on your mic and ask the question.
Yeah, it's okay. Thank you. And thank you so much, Sharon, for that presentation. I just had a question when you were talking about the equilibrium and you were talking about the wave example. How do you ensure that if there are parameters of the equilibrium that they're being met and that the micro scale or the agent doesn't negatively impact the macro? So going back to the stadium wave that people do, how do you ensure while the wave is going around that there's no disruption then creating another wave simultaneously? I was just wondering what your thought is on that. Applying this to real life scenarios, there's gonna be a lot of disruptions. So I was just wondering what your thought is.
Let me maybe share my screen. I'm not sure whether I get your question. Let me go back to the slides. So for game theory, I think there are 2 steps. The first is to model what the natural phenomena is there. So then that requires us to actually calibrate the game so that the outcome of our model can match the reality. And so that requires the calibration of the reward function or the objective function I mentioned here. When we say if we want to use this mean field game objective function to model human driving behavior, so then we have to really calibrate what terms should be included in there. So what the human driver really care for, and then what's the weights among all these terms. So that's one aspect. The second aspect is because I use mean field game to control AVs, and since it's under our control, basically we can design them so that they can behave in a way that achieve our goal. So to do that, we need to carefully find an objective function that can mitigate the traffic flow pattern. So that's our goal. in this case, basically we design this objective function be like here. So we add these two terms, and we found out that this design can actually help the mitigate the emergence of the shock wave. And there are some work I didn't present is we also use this mean field game to model the mixed traffic. So basically we couple the mean field game and also some existing traffic model, actually is the ARZ model, which is a non-equilibrium model. So when we couple them, we also try to understand how we can design this reward and also the coefficients in front of this reward to make the traffic, the stop and go wave disappear as fast as possible. So does it answer your question?
Yeah, I understand the mitigating effect and creating this equilibrium. Basically, the question is, what if one of these micro pieces of the macro scale wouldn't function in a way that we would like to, basically not following the kind of vacuum situation. Would this vehicle then have to be taken out of the equation so that it doesn't impact the wave? Basically, that's my question.
I see. Yeah, so here we make a simplified assumption that all the agents are homogeneous. They are rational and they try to optimize their objective function. However, if one behave very different from others, so then that we can treat it as a disturbance or perturbation to the system. So then this agent is not probably anonymous anymore. It may become a major player of this system and then completely change the behavior of the system. So in this case, then we have to take out that agent and model its behavior and also its interaction with all other agents and see what may happen.
Yeah, that's exactly what else. Thank you.
A good question.
If you have questions, please raise your hand. Okay, so questions. Did I pronounce your name correctly? And you can open your mic and answer your question. Yeah, ask your question.
Can you hear me?
Yep.
Okay. So thank you for the talk. It seems to me like intuitively mean field game theory might be most justifiable when the interactions are local and something like, two at a time, and each agent is acting individually in a rational way. But if you have autonomous cars who can communicate with each other at longer distances or sort of coordinate with some sort of centralized authority, be it some operator in the cloud or whatever, how applicable is the mean field game theoretic analysis in that case to determining travel behaviors that might, say, try to mitigate a traffic jam or something like that?
Yeah, it's a very good question. So this actually comes to how we assume the A-ways behavior, and also when the connectivity is introduced, we call connected vehicles, how we want to control them. And there are two, I think, debates. So for example, like in academia or for the transportation, like a DOT, their picture is that in the future, car should communicate first, and then we can have a centralized controller to control their movement. But we can see from the industry perspective, like a Waymo, Uber, when they develop their cars, they treat their car as an independent agent moving. They rely on their sensors on the top of their car to pursue the environment and make the decisions. And say the Waymo cars in the neighborhood may be able to cooperate through some cloud communication, but it's not a centralized system for sure. the reason is because of scalability. So if you introduce thousands of the car, imagine if we replace every car on the road now by autonomous vehicles. So it's impossible for us to come up with one central controller to control everyone's movement. So that's why people develop distributed control. But from my perspective is that we need to find a correct motivation for why the AVs want to cooperate with its neighboring cars. Usually it's because they share some common reward function. Then basically if they don't cooperate, they get punished. But my argument is they may also be non-cooperative. So they play this so-called Nash game. Because if I'm an autonomous car and I pick up a passenger, my goal is to transport a passenger to his or her destination as fast as possible. Why would I care about reaching social system optimal to maybe sacrificing my travel time to benefit others? So there should be some motivation for all the cars to cooperate eventually in the future. But I feel at this moment, I prefer to treat each car as a non-cooperative agent that also solve their own distributed control. Does it make sense?
Yeah, I think the only thing I'd add to that is that the communication with the centralized authority that I was thinking about was more limited to just like getting data, for instance, from Google Maps, or having one car on one side of the ring road communicate with another car on the other side via a cloud provider, but not necessarily having centralized control per se.
Yeah, I think for example, when nowadays everyone uses the Google Maps for navigation, but Google provides us the background traffic, like the average travel speed on each road and the predicted travel time. But based on this information, as an individual driver, I try to find my shortest path. So that's why I still behave, even with the communication, I still behave selfishly. So and non-cooperative. So that's the fundamental assumption for us to build this mean field game.
All right, thank you.
Hey, Trisha has a question. She asks, does the mean field approach require centralized control?
Yeah, following up with my previous answer, no, it's actually distributed, decentralized control. So, however, we have to make an implicit assumptions. The cars can still perceive the traffic condition, like the traffic density, through some central traffic systems. So for example, I use Google Map or I listen to radio, and I know roughly what's the traffic condition in my neighborhood, and then I will anticipate the future traffic condition based on my anticipation and the information I have, so that I can adjust my optimal speed.
Any other questions? If not, I have a question for Sharon. It's for the human drivers, we all have our own personalities, and you can tell that from the Waymo car try to merge on the freeway. Probably it's not aggressive enough to accept the gaps, and therefore you have to exit the freeway. In the game theory modeling, if you want to have personalities for autonomous cars, in what way can you add this feature to the model?
Yeah, this is a very good question. So I think this is also like a active field now. I assume in computer science, people are trying to model this heterogeneity across the autonomous driving policy learning. I think if we've only limit our discussion to the mean field game, so probably in the objective function, when we design these different terms like safety, emission, congestion, so we can put different weights. But many, I think, when I talked with some economists, they said that, okay, maybe the cars in the future, their aggressive can be a option for the occupants to select whether this car want to behave aggressive or conservative. And also some other researchers even think about maybe the car itself can learn from their occupants some historical data and then automatically set up this aggressiveness while driving. So then that I think will make the mathematical modeling much more challenging.
And also it opens up a lot of other potential problems. You know, if the user set the parameters to be in a very aggressive range, and what happens if it has a crash when it tries to merge? Would that user be more responsible, or the manufacturer of the car, or the autonomous driving system? So I think it opens up a lot of other issues other than just the model, how to model this traffic and how to.
Yeah, exactly. Liability, ethics, fairness issues.
So, which is a good thing. That means there's a lot more research to be done. Good for graduate students and researchers to take it on.
Yeah, and also along these lines, highly cross-disciplinary. So then probably we have to work with social scientists, lawyers, computer scientists to answer all these new questions.
So in closing, any other urgent questions? So if not, we want to thank our speaker again, and thank you, Sharon, for a wonderful talk. And if there's no questions, then we'll stop here. And again, I would like to remind our students, do not forget to turn in your assignment through Canvas. Okay.
Thank you, Professor Zhang. Thank you, everyone. Take care.